Whenever I teach calculus 2, I always have the students begging me for more applications. Can't we do more physics? And I'm here to help. So never let it be said that I don't give you anything. All right, so we have some application problems. So we have a rain barrel catching water from a downspout, but also other material, i.e., leaves, sticks, dirt, etc. As a result, when the drain at the bottom is open, it immediately starts to get clogged and the draining process slows at an exponential rate. So it starts off great and then it just slows and slows and slows because more and more junk is getting caught in the drain. The exponential rate is given by R of t equals 100 e to the negative 0.5 t, where R of t is measured in gallons of water per hour. If the drain is left open, how much water drains from the barrel? Interesting. So you're just going to leave it open for forever. So did you catch that? So if the drain is left open, in other words, you're letting t go to infinity. You're just going to let it drain forever and ever and ever. How much water drains out from the barrel would be gallons. That would be your unit. Okay, then let's look at the rate that they gave us. So they're giving us a rate, and they're telling us that it's getting clogged in the rate of drainage right here, and it says it's gallons per hour. See that? So now we have to remember something from, well, Calc 1, but also Chapter 6. So let me make a comment here. Oh, and let me just say here, R of t is how fast, it's the rate of water draining, right? It's how fast from the barrel. Now, where am I going with that? Well, the thing I was about to remind us of. Okay, so recall from Chapter 6 that if you have the integral of a rate function, this is also, honestly, a Calc 1 thing. If you have the integral of a rate, it's the integral of your speed. It will get you how much? It will get you quantity. In other words, and we learned this back then, if you take the integral of q prime of t dt, that's equal to q of t, quantity, right? All right, so let me just box that. We've seen that before. It's the fundamental theorem of calculus, but with applications, right? So if you take the integral of a rate, you get the quantity. And we use this all the time for energy, power, work, force, etc. I mean, we don't really call it that at the time, but that's what's going on, right? Same thing with distance, position, and velocity. I mean, there's a relationship going on there. Velocity is a rate function, and you get distance out of it. Okay, now where am I heading with that? Well, because the rate of water, in other words, this R of t is q prime of t. I mean, I didn't call it that, but that's what it is. So this is my q prime right here. That's my rate function. So I'm going to integrate that. All right, so q of t, which is going to be how much, right? That's what they asked for, how much water, would be equal to the integral from 0 to infinity, right? Because it said t is going to infinity, so 0 to infinity. And of course, you can't go back in time before you open the drain unless you have a magical car. At least that's what Back to the Future taught me. All right, so of q prime of t, which is r of t. Right? Actually, I guess I could just say r of t. Here, maybe that'll be easier. Right, that is the derivative, which means I'm going to be taking the integral from 0 to infinity of that function, 100 e to the negative 0.5 t dt. Okay, let's do it. So, I mean, the application is all the setup, right? Getting that set up correct. Once you have this, then you're just doing the same thing we've been doing through this whole section. So 100 times the limit, because of course 100 can come out. I'll use letter, I don't know, A this time. As A goes to infinity of e to the negative, oh, integral 0 to a e to the negative 0.5 t dt, like that. So I'm taking the limit of this integral. Okay, so that would be 100, except my zeros got smaller and smaller as I wrote, 100 times the limit as a goes to infinity. And then I'm going to integrate this. So that'd be e to the negative 0.5 t times 1 over negative 0.5. Again, it's actually a baby u substitution, but we're past the point of having to show the work for those all the time. We've got other things to do. But if you want to, right? That's what you're doing, right? And skipping the middleman, right? Okay, so then a negative power really means it's 1 over. So I'm going to substitute and rewrite this a little bit. So this is 100 times the limit as a goes to infinity. Actually, it's not 100. Watch me. 1 over negative 0.5 is 1 over negative a half. 1 divided by negative a half would be negative 2. So it's negative 200. Limit is a goes to 0. And then I'm going to do e to the... I'm just worried about losing everybody. Let me do this. E to the negative 0.5a minus e to the negative 0.5 times 0. Like that. Okay. Now, if you need to make a note of where that came from, it came from over here. So 1 over negative 0.5 is 1 over negative a half, which is negative 2. Right? That's what's going on there. And notice there's no more than 1 over negative 0.5 in front, right? Because I factored it out. All right, so then let's rewrite this. This is negative 200, limit a goes to infinity. I'm still stuck there. 1 over e to the 0.5 times a. And then this is e to the 0. E to the 0 is 1, so that's minus 1. Okay, so now I can put infinity in, finally. This is negative 200, and then I'm actually going to put in infinity, kind of. I mean, it's not really putting in, it's more like logically thinking it through. So if you put in infinity in here, like that, e to the infinity is infinity, and 1 over infinity is 0. So that whole thing is 0, minus 1. So it looks an awful lot to me like you have negative 200 times negative 1, which is 200 gallons. So if you leave that rain barrel open forever, 200 gallons will drain out of it. We can check in Desmos what we're doing here. So we have that lovely function. There's our rate function. And then we're integrating. And of course, we cannot go to infinity, but we can say integrate from 0 to a of r of x dx. Oops, r of x dx. I just made it x instead of t, just for convenience sake. And then I'm going to let this go from 0 to 10,000, say. Let's just see what happens. And that integral, whoop, it became 200. Did you catch it? It gets to the point where even Desmos is like, I'm not dealing with this anymore. There's not enough decimal places to make it worth my while. So I'll even make this smaller. I'll make it like 1,000. There we go. Amazing, isn't it? Even at those values, it's still 200. It just shows you that this one really was 200, and you can spot it. All right, wonderful. We're done and have proven that one. And of course, as with all physics problems, we don't want to forget our unit. And we don't have to say it's convergent. It's obviously convergent. Story problems like volumes and things like that, they wouldn't give them to you generally unless they were convergent. Unless they ask you, is this divergent? Ha ha ha. I gave you an impossible problem.